Hey everyone, welcome back. Today we're talking about something that lives deep under the surface of your code, but can have a real impact. The difference between big Endian and little Endian byte ordering, and why it matters in C++ programming. Let's start with a simple question. What does Endian even mean? In computing, Endianness refers to the order in which bytes are arranged in memory when storing a multi-byte data type, like an int, float, or double. Let's take a 32-bit integer as an example. This value takes up 4 bytes in memory. Now, depending on the system architecture, those 4 bytes can be stored in one of two ways. Big Endian, which means most significant byte first, and little Endian, which means least significant byte first. In big Endian, memory will look like this. But in little Endian, memory will look like this. Same integer, different byte order. So which is more common? Most modern systems, including 32 and 64-bit architectures, basically all consumer desktops and laptops, use little Endian. But that's not universal. Some network protocols, embedded systems, and legacy hardware still use big Endian. Which means if you're writing C++ code that talks to other systems, writes binary files, or works with low-level memory, Endianness matters. How can you see this in C++? You can actually inspect memory layout using a little code. If you run this on a little Endian machine, you will see this. That's the least significant byte first, little Endian. On a big Endian system, you would see this. Why does Endianness even matter? It might seem like a low-level technical detail, but there are a few situations where getting this wrong can completely break your program. Let's go through the main ones. If your program writes raw binary data to a file, and that file is read by another system, you have to agree on a byte order. Let's say your C++ program writes integers directly. Now, someone on a big Endian machine tries to read that file. They are going to interpret the bytes differently unless they know the format. This is why most binary file formats, like PNG and others, define a fixed Endianness, often big Endian. It ensures consistency across platforms. Another big one is networking. The internet uses network byte order, which is big Endian. So if you are sending data over a socket and your machine is little Endian, you have to convert. That's where functions like these can come in. Without this conversion, two computers might completely misinterpret the data they are exchanging. If you are writing a custom serialization system, maybe for a game engine or distributed app, you will need to define an Endianness and stick with it. Otherwise, one client might send little Endian and another might receive big Endian. Suddenly, all your positions, scores, or timestamps are scrambled. In embedded systems, you don't always get to choose your architecture. Some chips are big Endian, others are little. Some can switch. So, if you're writing portable code, like a library that might run on different chips, you need to account for Endianness. Same goes for firmware updates, low-level drivers, or cross-compilation scenarios. Ignoring Endianness can lead to silent bugs that only appear on specific hardware. There is no standard C++ macro for this, but you can detect it like this. It works by checking whether the least significant byte is stored first in memory. If you are using C++ 20 or later, there is a cleaner way with the bit header. That's the modern standard way. To convert values between big Endian and little Endian manually, you will need to swap the byte order. Here is a simple function for a 32-bit integer. This rearranges the byte explicitly. There are also compiler intrinsics and built-in functions for this. Be careful when writing structs directly to disk or over the network. If you just dump this struct into a binary file, you're not just risking Endian issues, but also alignment, padding, and compiler-specific layout. The best practice is to write each field individually, in a known order and format, and convert the Endianness manually if needed. Thus changing Endianness hurt performance. Not much. Modern CPUs can swap bytes very fast. But it's still a good idea to minimize conversion and only do them at boundaries, like file input-output or network transmission. Inside your application, you can keep everything in native format for speed. and only convert when importing or exporting data. So which one is better? That's a bit like asking, is driving on the left or right better? Both Big Endian and Little Endian have their merits. Big Endian is more intuitive to read. Most significant byte comes first, just like with right numbers. Little Endian is easier for incrementing and certain bitwise operations. But in the end, it's not about which is better. It's about being aware and consistent. Let's wrap up with a few practical tips. First, know your platform. Check your system's Endianness if you are doing low-level work. Second, never assume Endianness in portable code. Always detect or define it. Third, when saving binary files or sending data over the network, pick a standard Endianness, usually Big Endian, and stick to it. If you are dealing with byte buffers, write functions that handle Endianness for you. If you can, test your code on both Little and Big Endian systems, or at least simulate them. Endianness is one of those things that seems unimportant until it breaks something. It's not something you think about every day, but if you care about portability, networking, performance, or just writing robust, low-level code, you need to understand it. C++ gives you the tools, now it's up to you to use them correctly. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.